guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to the topic of electrochemistry, and from the term itself you probably can guess that it involves electrons and chemical reactions. So basically electrochemistry involves electron transfer in these different reactions, where a chemical reaction produces an electrical current. And so we're going from chemical energy to electrical energy. Or basically, electric current causes the chemical reaction. So electrical energy causes the chemical reaction. So as you can see, it works both ways. So the two terms that you have to get really familiar with is oxidation, which is the loss of electrons, and then reduction, which is the gain of electrons. So the way in which a lot of people like to remember this is oil rig. At least this is how I like to remember it from high school. So oil rig stands for oxidation is loss of electrons, and reduction is gain of electrons. So this is a really good mnemonic to remember. So let me show you an example of a reaction that occurs where there's an oxidation and reduction that's occurring. So in a reaction between permanganate, MnO4-, and iron 2+ in water, and in this process, we have protons that are involved. And this goes to Mn2+ as the ion, Fe3+, and water. So as soon as you see this reaction, the first thing you want to do is balance it. So when you actually end up balancing the reaction, it ends up being 5 iron 2+, 8 H+, 5 Fe3+, and finally 4 H2O. So when looking at a reaction like this, we want to separate it into two separate half reactions. And this makes it easier to figure out which is the oxidation and which is the reduction. And don't worry, I have this diagram right here, but I will explain that in a moment. Okay, so let's separate it into MnO4- plus 8H+, going to Mn2+ plus 4H2O, and the other one being 5 Fe2+, going to 5 Fe3+. So in this case, the one that's easier to look at is probably going to be the iron 2+ going to the iron 3+. So when you look at this equation, how many electrons are being transferred? So if you start out with 5 times 2+, this has a charge of plus 10, right? And if we look at the iron 3+, we have 5 of those with a charge of plus 3, so we have plus 15. So for something to have a plus 10 charge and then become plus 15, it means that it must have lost electrons, right? And so it lost electrons, and there's 5 electrons that were transferred. And since this is losing electrons, this is going to be the oxidation reaction. On the other hand, let's look at this other one that's up here, where we go from MnO4- to Mn2+. So right here, the first thing you have to figure out is the oxidation state of this manganese. So the way in which we can figure that out is by looking at this whole molecule. So for MnO4-, oxygen has a charge of -2, right? You can figure that out by looking at the periodic table, and for every group, you can tell what kind of charge it has. So for example, in group 1 elements, they all have a charge of +1. For group 2, they have a charge of +2, etc. And then when you go from the other side, starting with the group with fluorine, you start out with -1, and oxygen, which is in the group to the left of that, has a charge of -2. So -2 times 4 is -8, right? And then the overall charge of this molecule is -1. So the charge on manganese plus -8 is equal to -1. So what could the charge on manganese be? You're correct, it has to be +7, because 7 minus 8 equals -1. So the manganese oxidation state is 7+. So now when we look at this, we're going from manganese 7+ to manganese 2+. That's the difference in the charge. So now we can see that we're going to put 5 electrons on this side, right? Because 5 electrons would be subtracting 5 from the 7+ to make it 2+. So I'm going to squeeze that guy in here, plus 5 electrons. And since you're adding 5 electrons here, this is going to be reduction because you're gaining electrons. So this is going to be the reduction equation. So as you can see, when you get a redox reaction, which means that you have a reaction with both oxidation and reduction, you want to separate it into the two half reactions so you can see where reduction is happening and where oxidation is happening. So right here I showed it via math how we separate these long redox reaction into the two half reaction, but in reality when we actually do it in an experimental setup, we physically separate them with a wire to allow electron transfer to produce a current that can do useful work. And so now let's look at this setup. Electron transfer is going from this electrode, which is called the anode, to this electrode, which is called a cathode. In this diagram, let me draw these arrows in to avoid confusion. At the anode, you can see that zinc, the metal, so this is solid, is becoming zinc 2+, which is aqueous. So it's getting released into the solution. So in this case, 2 electrons are lost, right? So this is oxidation. So oxidation always occurs at the anode. So now these electrons that were lost, these 2 electrons, go into this circuit through the wire and travel from the anode to the cathode. And in the process, it goes through a voltmeter that can measure the current. So it goes and flows into the cathode, gets gained by the copper 2+ in the solution, and forms solid copper. So at the cathode, we have reduction occurring. Where in this case, for this experiment, you would have solid copper forming on this electrode because as the electron keeps flowing, it's going to add more electrons to the copper ions in solution to create more solid copper. But electron transfer from one reaction beaker to another will stop due to charge buildup, and that's why we have something right here called the salt bridge. So we add a salt bridge to allow for ion transfers so that the two solutions stay neutral. If this didn't exist, all the electrons would just keep accumulating in this beaker, right? And the flow of electrons would not be possible. But by having a salt bridge, which has different ions, for example, in this particular picture, it has potassium plus and chlorine minus. This can also be NaCl, any kind of salt that can break up into its corresponding ions. So this is an example of a galvanic cell. And what it's doing is it's changing chemical energy to electrical energy, like I showed you right here, and that's the whole point of electrochemistry. And so this chemical reaction of oxidation and reduction is creating electricity. So the reaction takes place at the surface of these individual electrodes, and the thing you have to remember is that the left one is the anode, where we have oxidation half reactions that occur. So remember, we split them up into oxidation and reduction, right? And on the right-hand side, we always have the cathode, which is where reduction occurs. So we can also write out the potential difference between the electrodes as being delta, and this Greek sign is the potential of the right, or rather the anode, minus the potential of the left-hand side, or the cathode. So this change in the potential is going to be positive, since electrons always flow from the left to the right. Since oxidation is happening at the left, the lost electrons always have to flow to the right where something gains it. So this is always going to be positive. This value also depends on how much current is flowing, and maximum potential is achieved when the process is reversible. And when we approach the limit where we have the maximum potential energy difference between two electrodes, this value, or potential energy difference, is known as electromotive force, also written as EMF. And electromotive force can also be called the cell potential, which is just given the value of E. So this is cell potential. So this quantity is related to the tendency for an element or a compound or an ion to acquire or release electrons. So the maximum potential in this scenario can be figured out, and it will be given the sign EMF or E cell. So like the diagram before, where we had two beakers, we can't measure electron transfer of just one cell. So what we can do, if we only have one system that we want to look at, is compare electron transfer of all cells, or half reaction, with respect to the hydrogen electrode. And so the hydrogen electrode is often called SHE, or SHE, which stands for the standard hydrogen electrode. And based upon the standard hydrogen electrode, we have standard reduction potentials, or E0 values, that are tabulated for compounds with respect to the standard hydrogen electrode. And so as you can see, this is the standard where the E0 is going to equal 0. And so for any other metal that you put in the other beaker, you can get the reduction potential with respect to this. So we're going to have positive values up here, which is a cathode with respect to the SHE, and we have anodic halves with respect to the SHE down here. And so as you can see, this is the same exact setup as what I just showed you before, with oxidation happening on the left-hand side. In this case, we have another half reaction of zinc going to zinc 2+ and losing 2 electrons. The electrons flow through the wire, the voltage is read by the voltmeter, and then it's transferred to the SHE cathode. And so in this case, the reduction that's happening is 2H+ gaining 2 electrons to make hydrogen gas. So from here, the potential energy difference for the whole cell can now be written as E cell is the E of the cathode minus the E of the anode. So in this example, what would E cell be? Well, for the cathode, we have this zinc reaction, and we can find it right here. So in the zinc reaction, we have zinc going to zinc 2+ plus 2 electrons, and the value is negative 0.744. But since these are reduction potentials, we have to actually flip the sign, since oxidation is going to be the opposite reaction to reduction potentials. And so we're going to make this positive minus the anode, which is just the hydrogen electrode, which is 0, and we get an E cell value of plus 0.744. As you can see, since it's a positive value, the reaction is spontaneous, and the voltmeter reads a value very similar to this. The reason why this might be slightly different from this is because depending on the reaction, it's not going to be 100% efficient. The standard reduction potentials might be slightly different, but as you can see, they're very similar in value. So the standard reduction potential gives voltage differences between two standard electrodes, which is always the same. So this value is an intensive property. The reason why it's an intensive property is because the voltage difference is the same and does not depend on how many times the reaction occurs. So it can keep going, and this value is not going to change. So this value also stays the same when the half reaction is balanced. So that's why one of the half reactions has to be reversed if the sign of E0 changes.